Some models are cool. Not those models. I actually find that particular cultural institution pretty peculiar. I'm talking about the kind of model that lets you experience things you otherwise couldn't experience. Maybe it's something that's too big to see all at once, like our solar system, or too small, like a cell, or something that unfortunately doesn't exist, like the Millennium Falcon. Or something that would just be way too dangerous to have in your office, like a trebuchet. Sometimes it is difficult, maybe even impossible, to really understand things fully without making a model. But models don't have to be three-dimensional objects. In scientific terms, a model is anything that represents something else, whether it's physical or conceptual, in the same way that musical notes on a page are a model for music. The same goes for chemistry. Chemists use many models or simplified versions of reality to help them understand atoms and their interactions. Because the universe is weird. This ball and stick model is one idea of a molecule, perfectly spherical atoms connected by clearly defined bonds. This version of a molecule is a great way to begin understanding chemical bonds. But I gotta take you beyond beginner stuff to understand some models that explain bonds with more delightful complexity. Digging into the details requires models that are more complicated, but also more fascinatingly awesome. So while this episode of Crash Course Chemistry won't involve any Brazilians in swimsuits, I promise you will not be disappointed. It turns out that chemical bonds are not like little sticks at all. Bonded atoms, molecules, are more like groups of atoms hanging out just like close to each other because that's where their energy is minimized. So if I tossed all these models of atoms into the air and let them fly apart from each other, it's cool and fun for me, but those little balls would also have a lot more energy, and that's not the ideal situation for an atom, now is it? In reality, the only thing connecting two atoms together in a chemical bond is a bunch of electrons, and they don't sit still between the atoms gluing everything together. Instead, they're in constant motion, zooming all around the nuclei in a somewhat predictable pattern. In a covalent bond, the bonding electrons spend most of their time between the nuclei, and the nuclei stay close together because they're attracted to the electrons. And honestly, this concept of electrons holding everything together is itself just another model, an idea that represents molecules in a way that can be visualized. And it's a more accurate representation of reality than the ball and stick model. But the ball and stick model isn't useless. It helps us visualize and understand many important things about molecules. It also looks pretty cool. Imagine if, instead of making generalizations about how chemicals behave, like water dissolves salts, you had to memorize every single behavior of every single substance. No one would ever get anything else done in their lives. We generalize so that we can free our minds to do bigger and better things. So make no mistake, some models are great even though they're oversimplified to the point of being outright lies. It's important, in fact, to realize that all models are imperfect to some extent. I mean, think of the human models that people compare themselves to. Do you think that women in underwear catalogs and the guys in those black and white cologne ads look like that on Saturday morning after a long night of doing whatever models do on Friday nights? In fact, if a scientific model were a perfect representation of reality, it would cease being a model and become reality. So in addition to understanding how a model represents reality, you also have to recognize the ways that it doesn't represent reality so that you don't base a bunch of incorrect assumptions on it. Unfortunately, sometimes models aren't merely oversimplified, sometimes they are just downright wrong. And the chemical bonding model is no exception. Over centuries, it's been updated as experimental results have provided information about how the universe actually works. Early scientists, including Isaac Newton, thought that atoms combined because they were literally sticky, or because they had tiny little hooks on them like a kind of Velcro that held them together. That was their bonding model. In the 19th century, chemists like Berzelius discovered positive and negative charges associated with chemicals in certain situations. He and his contemporaries theorized that this was the force holding molecules together. That's a much better model than the first one, but still not entirely accurate, because they thought that atoms more or less attracted each other like magnets. Only after the discovery of electrons in the 1890s could chemists begin to understand the true nature of chemical bonds. Then in 1916, American chemist Gilbert Newton Lewis described a covalent bond as two atoms sharing electrons. Modern chemists still use this model as a simple way to represent chemical bonds on paper. A Lewis structure is a two-dimensional model that represents covalent bonds as straight lines and unbonded valence electrons, those in the outermost energy level of an atom, as dots. Inner electrons aren't shown at all, and although it was developed to explain covalent bonds, it also works for ionic bonds. In Lewis structures, bonds are formed by pairs of valence electrons called bonding pairs in the space between two atoms. Pairs of electrons that are attached to only one atom are known as lone pairs. As you probably remember, atoms are most stable when their outermost electron shells are filled. For many atoms, that takes 8 electrons, so it's called the octet rule. And if you're bracing yourselves for some exceptions to this rule, well, you are correct. Tiny little hydrogen can only hold 2 electrons total, not 8. That'll make more sense when you watch our upcoming episode about atomic orbitals. But also elements in the third row of the periodic table and below often have more than 8 valence electrons. Beryllium and boron are notorious for having weird numbers, like 6 or 12 electrons. So yeah, the whole octet thing is really more of a gentle nudge than a rule. Let's stick to rows 1 and 2 of the table to keep it simple. Let's say I want to draw the Lewis structure for sodium chloride. Sodium has 1 valence electron and chlorine has 7. Since sodium is a metal, this must mean that it's going to be